Let's explain what a VLAN is. Our VLAN, or our virtual LAN, is a logical partition on our layer 2 network. Multiple partitions can be created, allowing for multiple VLANs to coexist. And each of these VLANs is a broadcast domain, usually with its own IP network. Once we get into, and you can remember back to subnetting, this is where that comes into play to an extent. VLANs are mutually isolated and packets can only pass between them through a router. The partitioning of the layer 2 network takes inside a layer 2 device, and it's usually the switch. Okay, so this is where it's going on. It's taking place inside this layer 2 device. So it's taking place inside of our switch. And the hosts grouped within a VLAN are unaware of the VLAN's existence. They just think that they're on a regular LAN network. By having these VLANs set up, our network administrator can decide how to segment its networks. It can network it based on function, project teams, applications, without regard basically to its actual physical locations. Not everybody in a VLAN has to be located together. In the example here on the screen, perhaps not everyone in IT is in the exact same office. They may be scattered throughout the building. They may be scattered throughout a campus. Same thing with HR or sales or however it is that you decide to define your VLAN. On our switches, any of the ports located on this switch can belong to a VLAN, and any unicast, broadcast, multicast packets are forwarded and flooded only to end stations within that VLAN where the packets are sourced. It's not going out and looking at the other VLANs on that switch. It's staying contained within its VLAN. And each VLAN is considered a separate logical network, and the packets destined for stations do not belong to the VLAN must be forwarded through a device that supports routing. So if it's something that has come inside or you're sending out of your device on your network that doesn't belong inside that network, it will hit the device that will route it out to another location. A VLAN creates this logical broadcast domain that can span multiple physical LAN segments, and our VLAN improves the network performance by separating large broadcast packets or domains into smaller ones. If a device in one VLAN sends a broadcast Ethernet frame, all devices in the VLAN receive the frame, but devices in other VLANs do not. So this is how it controls some of that traffic and keeps our traffic overhead down. VLANs do enable the implementation of access and security policies according to specific groupings of users. Each switch can be assigned to only one VLAN, with the exception of a port connected to IP phones or to another switch. Let's take a look at some of the primary benefits of using VLANs. They are, like I've said, security. Groups that have sensitive data are separated from the rest of the network, decreasing the chances of confidential information breaches. And you'll see that here in this diagram. Here we have guest VLANs, we have students, we have faculty, so that only faculty information is shared together. Our students see each other, and our guests only see what we allow them to see. Cost reduction. The cost savings results from reduced need for expensive network upgrades and more efficient use of existing bandwidth and uplinks. There's better performance. When we divide our layer 2 networks into multiple logical work groups or broadcast domains, it reduces the traffic. Like we said before, things aren't going all over the place, they're going to where they belong. It shrinks the broadcast domains by dividing the network into VLANs. It does reduce the number of devices in the broadcast. We have improved IT staff efficiency. VLANs make it easier to manage the network because users with a similar network requirements share the same VLAN. And if you know if someone in, let's say, VLAN 20 here in this diagram are having issues, you're not going to go look at VLAN 10, you're not going to go look at VLAN 30, you're going to stay within VLAN 20 and look for the information there. You're going to see what the issue is in that segment. You have similar project and applications management. With the VLANs, aggregate users and network devices to support businesses or geographic requirements, and having the separate functions makes managing a project or working with a specialized application easier. If you know that only faculty is going to use a particular software or a particular application, whoever's maintaining your faculty VLAN, they're the ones who are going to have to know that. If you have different people managing different VLANs, then they only have to understand and know their applications. Each of our VLANs is a switch network, and it corresponds to an IP network. So VLAN design must take into consideration the implementation of hierarchical network addressing schemes, and that means that the IP network numbers are applied to a network segment and VLANs in an orderly fashion that takes the network as a whole into consideration. It's just not all willy-nilly within the VLANs when you assign IP addresses. There is a logic to it. Blocks of contiguous network addresses are reserved and configured on devices. Contiguous meaning that they are next to each other. You will see here that here in VLAN 10 we have 172.17.10.21, and is its IP address. It's on a 24-bit network, and you'll see here that this PC is also on the 172.17.10 network. The same goes here for our 20 and our VLAN 30. They are in the same subnet. In today's modern networks, we have distinct types of VLANs. Some of the VLANs are defined by traffic classes. Other types are defined by the specific function that they serve. We have the data VLAN, and the data VLAN is a VLAN that's configured to carry user-generated traffic. Okay, it's for the user-generated traffic. A VLAN carrying voice or management traffic would not be part of the data VLAN because it's data. It is user-generated traffic. Your default VLAN, all switch ports become a part of the default VLAN after the initial boot up, before you've gone in and assigned everyone to a VLAN. You can see this when you do show VLAN brief. You'll see that you have the default and you see all the ports on your switch there. VLAN 1 is considered the default VLAN. One of the security features is you go and you change your default from VLAN 1 because everybody's going to look at VLAN 1 to be your default location. You have native VLAN. It's assigned to an 802.1q trunk port. And the trunk ports are the links between the switches that support transmission of traffic associated with more than one VLAN. The trunk port supports traffic coming from many VLANs or tagged traffic, as well as traffic that does not come from a VLAN. It's untagged. And the trunk port places untagged traffic on the native VLAN, which by default is VLAN 1. That's why you want to change this up as part of security. Your native VLAN are defined in the IEEE 802.1q specifications to maintain backward compatibility with untagged traffic common to legacy LAN scenarios. So it's able to send in information that's coming from networks that you may not support. You have your management VLAN, and that's the VLAN configured to access the management capabilities of your switch. VLAN 1 is the management VLAN by default. To create the management VLAN, the switch virtual interface, or SVI, of the VLAN is assigned an IP address and subnet mask, allowing the switch to be managed via HTTP, Telnet, SSH, SNMP. And because the out-of-box configuration for Cisco switch has VLAN as the default VLAN, it should be a bad choice for your management VLAN. Change it up. In the past, the management VLAN for a 2960 switch was the only active SVI. On the 15.x versions of the Cisco IOS for Catalyst 2960 series switches, it is possible to have more than one active SVI. Okay, so keep that in mind. In the figure here on our right, all ports, like I said, are assigned to our default VLAN. Okay, now let's look at these different VLANs. We do have to have a separate VLAN to support voice over IP because it's a little bit different. It has to have assured bandwidth to ensure voice quality. The transmission priority over other types of networks, because if you're talking to somebody, you don't have to wait until another packet of data is switched through. You have the ability to be routed around congested areas on the network, and you have a delay of less than 150 milliseconds across the network. To meet these requirements, the entire network has to be designed to support voice over IP. And details on how to configure the network to support voice over IP we will not cover in this course. You just need to understand that it has to be done. The figure here on our right for VLAN 150 is designed to carry voice traffic, and you'll notice that the student computer PC5 is attached to a Cisco IP phone, and the phone is attached to the switch. So PC5 is in VLAN 20, which is used for student data. So here we see our PC is in VLAN 20. You'll notice here that our switch port is configured to support voice traffic. The port sends CDP frames to provide information used by the IP phone, and then the port forwards frames associated with VLAN 150, which is our VLAN for our phone. The switch is configured to support voice traffic using VLAN 50 for voice VLAN, and it prioritizes those calls for that device. You will have a packet tracer activity to complete on this. We also have VLAN trunks, and that's in the multi-switched environment. That means we have more than one switch in our network. The VLAN trunk carries more than one VLAN. It's usually established between switches so that the same VLAN devices can communicate even if physically connected to different switches. A VLAN trunk is not associated to any VLAN, neither is the trunk port used to establish the trunk link. With our Cisco iOS, we support the IEEE 802.1q, and that is a popular trunk protocol. Here's an example. We have our VLAN 10, VLAN 20, 30, we have VLAN 99, that is our management and native. It's been changed from VLAN 1, and remember we did that because by default the management and native is on VLAN 1. Here you'll see that the fast Ethernet ports 1 through 5 are 802.1q trunk interfaces with native VLAN 99 on them. Our Ethernet ports 11 through 17 are VLAN 10, our Ethernet ports 18 to 24 are VLAN 20, and our Ethernet ports 6 to 10 are our VLAN 30s. Our VLAN trunks are configured to support 10, 20, 30, and our native and management 99. You do need to keep into consideration that our VLANs wouldn't be very useful if we didn't have this trunking capability. It allows our VLAN traffic to propagate between switches. Like I've said, we can move our traffic across different switches so that the devices are the same VLANs, don't have to be located in the same building, the same area, the same campus. The VLAN trunk does not belong to a specific VLAN. Okay, so keep that in mind. It's very important to remember that. Our VLANs do help us control broadcast domains, and they're used to limit the reach of the broadcast frame itself so that it's not going into other VLANs. The VLAN is a broadcast domain in and of itself. The broadcast frame sent by a device in a specific VLAN is forwarded within the VLAN only. And this helps controlling the reach of the broadcast frames, their impact on the network, and the unicast and multicast frames are forwarded within the originating VLAN as well. Here's a good example of how things would work on a network without VLANs implemented. We'll see that PC1 sends out a broadcast message, and you'll notice that it goes to everybody on the network. So it floods the entire network with the traffic. However, if we have a VLAN set up, if we send out a packet from PC1, it should only go to the other PCs within that VLAN. So you see here that PC1 sent out the packet and it went directly to the other device within that VLAN. It would do the same if we had multiple PCs or multiple devices within that VLAN. It would only hit that particular device in those VLANs. Now we tag Ethernet frames for VLAN identification. They have to know where they're going. Frame tagging is used to properly transmit the multiple VLAN frames through a trunk link. Switches will tag frames to identify the VLAN they belong to, and different tagging protocols exist, with the IEEE 802.1q being a very popular one, and like I said, that's the one we use with our switches. The protocol defines the structure of the tagging header added to the frame. Switches will add the VLAN tags to the frames before placing them into a trunk link, and removes the tags before forwarding the frames through non-trunk ports. Once they're properly tagged, the frames can traverse any number of switches via trunk links and still forward within the correct VLAN at the destination. Now, a frame that belongs to a native VLAN will not be tagged, and a frame that's received untagged will remain untagged and be placed in the native VLAN when forwarded, because they figure it needs to go out. If there are not ports associated with the native VLAN and no other trunk links, an untagged frame will be dropped, so it won't be sent anywhere. With our Cisco switches, the native VLAN is VLAN 1 by default, so remember we make sure that we change that. Now let's take a closer look at this tag. The VLAN tag field consists of a type field, a priority field, a conical format identifier field, and a VLAN ID. Our type is a 2-byte value called the tag protocol. For Ethernet, it's a hexadecimal of 0x8100. The user priority is a 3-bit value that supports level or surface implementation. Then we have our conical format identifier. It is a 1-bit identifier that enables token ring frames to be carried across Ethernet links. And then we have our VLAN ID, and it is a 12-bit VLAN identification number that supports up to 4096 VLAN IDs. Okay, so keep in mind the type is a 2-byte. Bytes is 8 bits. And then our user priority is in 3 bits, our conical is 1 bit, and then our VLAN ID is 12 bits. So keep that in mind. Now let's look at voice VLAN tagging. We'll see here that a switch port is configured to support voice traffic. It instructs the phone to tag voice frames with a VLAN 150. It prioritizes those voice frames. Remember, we don't want interruption in our telephone conversations. And it forwards data frames onto VLAN 20. That's what this one does. Here it is configured to tag voice traffic frames with 150. It's configured to send untagged data traffic. And then here it's configured to send untagged data traffic. Okay? So that's important to keep in mind.